So, quick introduction about me. Why this thing is not changing slide. All right, so my name is Claudio Contin. I'm a security consultant, penetration tester based in Wellington, New Zealand. I come from a web development background, mainly backend development and quite a lot of JavaScript, pretty much everything but CSS. In my previous role, I used to be a web developer trainer as well in terms of security, teaching OWASP 10 and secure coding guidelines. And I've also done small contribution to Beef Project and Go Fish. Some fun facts to start with. So this is my personal laptop at home. As you can see, my C key is a bit broken. That's why I make a lot of mistakes during my work, and I do Control-C a lot, as you can see. You probably guessed from my accent that I'm not actually originally from New Zealand, so I'm actually Italian. I was born and raised in Italy, and I moved to New Zealand around end of 2007. And always be surprised about the similarity between the two countries, especially looking at the shape. As you can see, they really match quite a lot. This is actually my hometown back in Italy. It's kind of based north of Milan. It's kind of well famous for stracciatella ice cream and San Pellegrino water. Whereas this is where I moved to, so this is actually Wellington in New Zealand. It is well known for its bad weather, and it's one of the windiest cities in the world as well. And talking about wind, this actually was the window in my bedroom, which exploded from inside out after a big wind gust I had early one morning. As you can see, the debris down the red card on there. So that's all part of the whole window that kind of died that day. During these few years, I lived in Australia as well. And yeah, I don't have many stories about that, just I made it out alive. So this talk is about Ruby. So Ruby is a 25-year-old language. It's really well known for the web framework Ruby on Rails. If you are in penetration testing, you will know Ruby for Metasploit. Everyone loves Ruby. All this metaprogramming magic that makes all those framework possible. So the agenda for today, I will start talking about Ruby gems and Ruby gems with the extensions. I will give a high-level overview of what fuzzing is. I will talk a bit about AFL. I'll talk about my setup to target Ruby gem with C extension and potentially Ruby itself. Talk about some of the findings. And I will give a brief introduction of our grammar-based fuzzing, targeting languages and Ruby in specific. So what Ruby gems are a way to create Ruby libraries, saying in simplistic ways. So Rails itself is a Ruby gem. So what happens when you want to install a gem, you type gem install, name of the gem, and what happens on the network level, your machine will contact gems, Ruby gems API, check what dependency the gem you want to install has, and download everything it needs to and install locally. The other way to install gems is to use gem file and bundler rather than typing gem install all your gems. And the way to use gems is just requiring them in your code base, simple as that. So when you install a gem with C extension, you often see this message. What it means is your machine is missing some libraries that the C extension needs. For example, if you're installing MySQL to gem, you will need leave MySQL development libraries installed in your box. So why developer wants to write C extension, Ruby gems with C extension? One of the main reasons is speed. So Ruby itself, the language itself, is not the fastest languages out there. So if you have some specific area where you're concerned about performances, you might consider writing it in C. Other reason is reuse existing C libraries and port them into Ruby. We'll see one of the findings I got is specific on one of these cases. And of course, when you write C, you have issues with, you need to be careful with memory corruption, memory leaks, and all this kind of stuff. So this is a really simple C extension. Of course, you need to include a ruby.header file. And for example, this would be a hello C extension class. And by default, you need to declare init underscore name of your class. And as you can see, Ruby define class will define a Ruby class hello, and Ruby define method will define a method word on the class hello. As simple as that. So when you create a Ruby gem with C extension, you need to create a extconf.rb file where you specify compilation option for your C extension. And the two main lines, the one require mff and create my file, are actually the two only required lines. Everything else are a compilation option you can specify at the top of the defaults. So after you create your C extension in your ext.conf, you invoke your extconf.ruby by using Ruby itself, which generates the makefile. And by having the makefile, you just compile your extension, which generates a share object at the end. And to just use it, you can do require, or you can do require relative. So the difference between the two is require relative will look for the Ruby or the share object in the current path, whereas the require will look in the your Ruby setup on your machine. And to user, you just use as a normal Ruby class. So this is a structure of a typical gem. So the lib part will typically contain Ruby code, and the ext part will contain native C code, and everything else is test and rec file. So API fundamentals about writing C extension is so discouraging of the use of malloc and free. So just keep in mind the API only discourages you. It does not prevent you to use malloc and free. Leave free to Ruby garbage collector. And one of the main key thing within C extension is this value type. So everything in Ruby is an object, and in C extension as well. So this value type is actually a pointer to a Ruby object within your extension. So the API never allows you to access Ruby objects directly. Instead, it gives you a pointer to these objects. And to understand what type of object within, what type of object this value type is, you can use Ruby type and say is an array, is a string, and so on. So why did I look into this? So when I joined, when I started doing pen testing as a full-time job, I always thought that binary was one of the main areas to concentrate on. So I wanted to learn more about exploit development itself. And in fact, learning is one of the main reasons I wanted to do this. And just looking at, looking at bounties out there, I realized that you can still find bugs. You don't have to write exploit necessarily. You can still, contribute, finding bugs, report the bugs, and as I say, contribute to the community. So exploit development is not necessarily if you want to do this kind of stuff. I chose Ruby because I worked with Ruby more than 7 years, so it was a easy choice. And again, Ruby itself and mruby within Shopify script is already part of bounties. Whereas I noticed that C extension, I couldn't find anyone doing much research on C extension. That's why I kind of digged into that area a bit more. So let's talk a bit about fuzzing now. So the main reason people do fuzzing is because code reviews can be quite hard to detect bugs often for complexity of the code. The main purpose of fuzzing is fire a lot of inputs to the binary and make the binary crash. That's really what fuzzing at a high level is. Root code analysis is the post-crash analysis of why the crash happened with this kind of input in the first place. And fuzzing itself typically requires little effort in most cases. Fuzzing mainly divided in two main categories, so dumb and smart fuzzing. So dumb fuzzing is where the input is randomly generated by the fuzzer. The fuzzer has no knowledge at all about the binary you're targeting. Whereas in opposite, smart fuzzing, they really target specifically per binary, and they typically require more effort to be set up. So in terms of type of fuzzer, as I say, they're really mainly divided into how the input is generated. So mutation-based fuzzer is where you provide simple inputs for the fuzzer, and the fuzzer will mutate those and target the binary. Whereas generation-based fuzzing is where actually the fuzzer knows more about the binary you're targeting, and it generates inputs itself. Evolutionary feedback-driven, they are more similar to mutational fuzzer, and how they work is they use instrumentation to understand that a new input reach some new code path. There are some new experimental type of fuzzer. They are called transformational-based fuzzing. So the idea of those is when you have some input checks in your binary, let's say you have a CRC check on the input you are providing to the binary, and a dumb fuzzer will never be able to pass this input check. So the idea of transformational-based fuzzing is that the fuzzer will mutate the binary itself, temporarily disable these particular checks, and carry on fuzzing with random inputs. Of course, this can create more false positives. As you can imagine, if you remove the input check and you get a crash, you still need to validate that the crash can be replicated by putting the input check back. So for this research, I use AFL, which is American Fuzzy Loop, was developed by Michael Zaleski, which is an ex-Google employee. And how AFL works is compile time instrumentation. So the main feature is it can detect that a new code path has been reached by the input you provide to the binary. And it really works best with reduced test case. So as you can imagine, if the binary has to parse the input you provide, smaller the input is, faster the fuzzing process would be. One of the features of AFL is dictionaries. So let's say you're fuzzing SQLite or any kind of language specific. You can specify a set of keywords that the fuzzer will use to generate inputs rather than generate completely random inputs. So other feature of the AFL is it can distinguish between unique crashes, which is really helpful when you get thousands of crashes, and they are really, at the end of the day, is really one unique crash. It makes it easy to kind of remove all the noise. When you use AFL, you can use defer mode, edge persistence mode, which is a way to kind of speed up the fuzzing itself. So how defer mode works is, for example, let's say you have a piece of code that does a lot of initialization process. You can put you can actually patch the binary and compile and saying, hey, AFL, when you start fuzzing a new process, please do not reinitialize the old process from this point until this point, and fork the process from this kind of state, and you will have faster fuzzing. And persistent mode is a similar idea where you use a single process to iterate through multiple inputs instead of one process and one input. You can use parallelization. So when you run AFL on multi-cores, by default, one AFL process uses one CPU. So you can spin it across multiple CPUs and multiple hosts as well over the network. You can, if you don't have the source code, you can use QEMU and some other project that allow you to instrument binaries without having, as I said, the source code. And AFL provides various utilities to check the various. So how does AFL does instrumentation? This is a really high level of AFL instrumentation. So it does insert some code within your binary to kind of notify whether if a new input reached a new code path within the binary. And how does it do it? It generates an intermediate assembly when you compile using AFL, GCC, or Clang. And if you're curious to know how it does it, you can use this AFL keep assembly at compilation time, and it will keep you this intermediate assembly. So now what? I wanted to target C extensions, so I could compile the C extension itself with AFL, but that wasn't really ideal, which meant I have to write each fuzzing test case manually to target each particular logic in the C extension. And one of the things is to keep in mind is often gems with C extension only have small component written in C, whereas the rest is written in Ruby. So why I couldn't just use Ruby? And because AFL wants the binary you calling, which in this case would be Ruby itself, I would just compile Ruby with AFL to start with. And this would be my fuzzing input. So I would require my extension. I would open the input file provided by AFL and fuzz the extension, as simple as that. So in order to understand if my setup was working, I created this really simple vulnerable C extension where I wanted to prove that all this setup was working. And within a minute, I got a crash. So I was pretty confident everything was good to go. So learn from mistakes. One thing to keep in mind is AFL does not give you the result of the binary. So when you fuzz a binary with an input with AFL, you don't know what the result is. You only know if the binary crashes or not. So when I was running this against Nokokiri with this famous XML parser in Ruby, and is also a big code base, I wasn't getting anything out of it. It was AFL was keep telling me that he couldn't find any new code path, and stupid enough, I realized that I wasn't giving enough memory to AFL. So yeah, so learn from mistake from here. So final tweaks, I could run all of these on my base OS, which is probably a bad idea. Also, I want to maybe try to target different Ruby version, different Gem version, and use maybe different compilation options for AFL, and for example, use address sanitizer, AFL, GCC, Clang, or whatever. I could use VMs, but yeah, VMs are a bit of a pain to copy and clone and stuff like that. So I ended up creating a bunch of Docker containers, which are all available at this URL if you're interested, and that was really my kind of setup in terms of machines. So this is what I use for defer mode with AFL. So this is the main.c Ruby code. So this is the source code of Ruby. And what I did here, I skip all the initialization code of Ruby, and I say when AFL wants to start fuzzing a new process, it just starts from this point. It will make fuzzing faster. My Docker setup is really simple. I just install all the dependencies I need, download and compile AFL, set environment variable to compile everything with AFL, download Ruby, patch the Ruby main C as I just showed before, and compile with AFL. So this is what it looks like. So I'm inside my Docker container. I install a gem with C extension. I create my fuzzing entry point. And I create a simple test case. And I let fuzzing running, as simple as that. I can skip this. So all was set up now to start actually looking into something. I didn't really know what to fuzz to start with. I wasn't too aware of too many C extensions, so I found out about this Ruby Toolbox website that collects a lot of nice gems. So I kind of picked few C extensions from this. And I start targeting mainly parsers. This is the hardware I use, which is my own personal laptop, which is, yeah, it's probably not best idea to use a laptop, but nothing else. So my first target was with CSV, which is a pure CSV parser. I was still trying various CFL option while running this, and with the 20-second running AFL on this, I got a crash. So I thought that something was wrong with my setup, because having a crash in 20 seconds is really probably uncommon. But instead, it was actually a real case. So by doing some root cause analysis in the code base, I realized that there was a double free condition in this case. So there was condition if one line was backslash, it was freeing the line, and it was freeing the same line afterwards. So in this case, I submitted a fix to the maintainer. It was merged without any changes, which is surprising, considering I'm not a C programmer. So, and so I want to give a really quick overview of a double free on a heap is. So when you free a chunk in your heap in glibc, will end up in a bin. Usually it's a double linked list. And when you double free the same chunk again, the same chunk will end up in the double linked list. What it all means is the first time the chunk gets reallocated, the user get access to the pointer to the memory address, and the same chunk is still in the actual bin. So what it means is you're actually able to control the pointer of the chunk within the bin, which means you can control it. Traditionally, you could exploit this by changing the forward pointer and backward pointer of the list by writing arbitrary memory addresses and achieve code execution. In modern libc, this is not really easy anymore because there are corruption memory detection built in. Of course, this might not be the case if you use embedded systems or if you disable those checks. You wonder why you should disable those security checks. Doing some research online, I found some interesting things of companies suggesting that you should remove those checks, which is a bit shocking. So yeah. So instead of fixing the code base, we were just suggesting, hey, just remove the check and carry on. And please don't do this. Don't follow those suggestions. They're bad. So moved on. This is was my next target. So OX is a fast XML parser. Has a lot of features. I will not describe them all. And this on the last line is one of the input that AFL generated after 5 minutes. And I got a crash pretty soon as well on this one. So in this case, it was just a null pointer. So the function was returning null, and the code base expected a struct, and nothing too interesting. The process just crashed. And the fix of the maintainer was just check that this variable isn't, if it's null, just exit gracefully rather than crash the process. And I target another functionality of this OX, which is a SAX parser, and within a few hours I got another crash, and this looked a bit more interesting. So I got a stack-based buffer overflow. As you can see, the memory address has 4 A's up there, and even running AFL with address sanitizer, I got the confirmation that it was definitely a buffer overflow. So quick note about address sanitizer, a fast memory error detector, and it can detect this kind of memory corruption. So the input that generated this was a bunch of carriage return character followed by a bunch of A's. And doing a quick debugging with GDB, I noticed that the string and copy was using n, which was set to this huge number, and it was kind of overflowing the destination buffer in this case. So I will probably skip this because I don't have enough time, sorry. So after the first buffer overflow was fixed by the maintainer, another off by 1 error was still present in the code base in a different place. And there actually was the same input generated the condition. What I did in this case, I worked with the maintainer I provided him the Docker container I was using to test this, and it kind of promptly fixed the issue after a couple of days. So after this, I decided to move into more JSON stuff after having a look at CSV and XML. I thought, well, why not try some JSON? So I target this. It's called yet another JSON library, which is actually an existing pure C JSON parser. It's been ported into Ruby. And also this gem has a bunch of features. One of those is supposed to be as close to crash proof as possible. So I've never thought I could find anything on this one. And I got a couple of crashes within a few hours as well. So this was my typical fuzzing entry point, and this was the input file that AFL generated for crash the binary. And the output I got is this one. So I got that this should never happen. So yeah, I'm not sure why that happened. And another second session failed as well from similar input file. I'll probably skip some of these, but just a quick note of what assert is not a mechanism for handling errors at runtime, and is often disabled when the code is actually shipped for production use. And what I did in this case, I reported as usual the issue on GitHub, and I provided the reproduction step, and a fix was released. And the maintainer actually contacted me directly and say, can you please make sure that the next time you disclose this privately? So I was a bit surprised considering that it was a public project. I just opened an issue on GitHub. I realized that this guy was the actual development manager of GitHub, and this gem is used by, it was downloaded 21 million times from Ruby gems. And he's also using some Debian Engine 2 packages, so you can actually apt install this Ruby YGL, whatever you pronounce it, which I never knew about. And after a few weeks, GitHub released this, introducing security alerts on GitHub, which is a good timing. How it works is, so if you enable dependency graph on your Ruby or JavaScript project, GitHub will tell you that if some of your dependencies have some no vulnerabilities, so it's pretty cool. And you can also set up various options, get notified by mail every time a new vulnerability comes up, something like that. And this is what it looks like in the interface. So. This is a blog post came out from GitHub a few days ago, actually, and they reported some statistics about this feature. And they say that within 500,000 of their repository, they found 4 million vulnerabilities in dependencies. And 450,000 of them were actually already resolved by project maintainers. To kind of put all of this in context, I set up a simple Rails application that includes all these vulnerable gems. And the thing I wanted to emphasize is that even though some of those vulnerabilities might not be exploitable in order to achieve remote code execution, but the whole process crashes, and the whole process in this case will be your application server of your app, right? And it's really hard often to track down those issues because there are no information in Nginx log or your whatever web server logs you use. There is nothing can be logged in your application logs. And in my setup, I use Puma and Passenger to kind of try out a few different options by crashing those application servers. And Puma does not log by default. So also by checking some open source Rails apps, I noticed that the Puma configuration doesn't include logging by default. And yeah, so what I did, I ran the app and replicate the crashes within the app. So in the case of the CSV, nothing was present at all in the Puma logs. So the application server was crashing, and there was no trace whatsoever anywhere in the logs. In the case of OX, there was some logging in there, which is good. In case of the buffer overflow, there was some logging, but there was nothing really useful to understand why and what was going on. And in case of the JSON one, it was kind of clear enough in the logs as well. Good thing about Passenger as well is Passenger logs by default, and all the back traces of this crashes were present. So again, probably would help you in case you have to dig into this kind of issues you might experience yourself. Quick note about memory leaks. So memory leaks is when a memory gets allocated and is never been freed. I will skip some of this stuff because I'm running out of time, but I want to mention this because I experienced this myself. When I was working as a dev, we used to get about once or twice a day some really weird exception in our code base that didn't make any sense. So every time the session was showing something totally different, I didn't point to any of our code base to actually give an idea what was going on. And that turned out to be actual memory leak in Nokogiri libxml specifically. So this is the same case that Envato experienced. So Envato is an Australian company. They have a big Rails code base. And they wrote a blog post about this, and they made really good points. They spent months and hours into looking into this. So as you can imagine, it would be a huge cost for a company to track down all this exception. And one last point, good point they make, is that the application server should have a seg fault. If it's seg fault, that should be the first priority for everyone to look at. So what's next? I realized that there was not so many C extension out there, or anyway, nothing new that was being pushed out or maintained anymore. So I thought into looking into fuzzing Ruby itself. And of course, when you use AFL against Ruby, it's good, but if you want to actually fuzz the actual language itself rather than the parser parts of the language, all the AFL inputs will generate something that is syntactically incorrect, so the Ruby will never even run the input test generated, right? So that's why I started looking into this concept of grammar-based fuzzing. And I'm looking specifically into this ANTLR tool, which has been developed by a professor at the University in San Francisco here. The main idea of NTLR is creating grammars. You can create parser and lexer rules. I would, skip this a bit. And this is what a Ruby lexer rule will look like as a high level, and this is a Ruby parser. So let's say a function definition will look like something like this. I skipped this. And there is a really nice tool out there called Grammarinator, which was developed by Renata Honodovan from University in Hungary, which use ANTLR to generate syntactically correct random tests to actually fuzz languages. This is based on ANTLR, and it create test generator in Python 3 language. And to really give a quick overview, it's really, really simple to use. Once you set up your grammar, you can just invoke this tool, which generates your Python and parser and a lexer, which then will be used to generate your random inputs. So this is a really quick output of this tool used against Ruby, so a bunch of definition. And one interesting thing to note is this code base is actually syntactically correct. So some final thoughts. So you don't need to be an expert. I wasn't an expert when I was looking into this. It's actually my first time doing fuzzing. You don't have to have the best hardware. As you can see, I use my own personal laptop. It can be, once the initial setup is done, it can be kind of semi-automated. I believe that if you have some kind of C code base within your organization, you should look into fuzzing and doing continuous fuzzing against it. And I believe that fuzzing cannot replace code reviews, of course. And one thing I would like to note is maybe public project hosted on GitHub, GitLab, or whatever could maybe those providers could allow to open issues privately rather than report vulnerabilities to the public. Yeah, that's probably about it. I'm run out of time. So thanks.